Swayam Prabha. Digital India. Educated India.
Right? I don't, in the summation I don't write y not equals to x, because my set S is defined in that way, right. So, this is the, these are the bunches of y's that would add up to the count of x. Fine. Now, see this frequency, whatever was kind of the quantity in the frequency that was pushing up the value, dependent on S. So, that quantity is also a random quantity. Who dictates that? Your choice of the hash function. Now, if your hash function was really good, then this x or y should have been uniformly distributed in the range of the buckets of size B. So, what was your hash function doing? Taking this universe U, mapping it to B. Now, the probability that if you pick any element x or any element y, that it would go to any location, a particular location, is uniformly at random. So, that is kind of a probability of 1 by B, right, because you have B buckets. So, if your hash function is good, I can write this as and then you can write this as n by b. So, you can write, I am kind of maybe hand weaving a little bit, but so you can write this if, as I said, if hash functions are good. You understand what I mean by good. Now, the trick is you set B to 1 by epsilon. So, you have now bounded your overestimate by fx plus n by epsilon. Mind you, that zone was that thing only. So, no element will get into the count whose frequency is low, because it cannot now cross the barrier of, so think of this, think over this frequency line, right. What I have done is, for each element given you an overestimate. Now, I would have been in problem if an element in here being overestimated landed up there, I would have counted it. But this small calculation that I did for you, and in which the random choice of the hash function, these good hash functions helped me, made it sure that no element here, this element here would also be overestimated, but it would not cross this barrier, because your overestimation is by an amount of epsilon n. Here is that quantity sitting. So, that was the trick in the choice of B. So, that is 1 by epsilon, and an analysis which I had not get into is the analysis of the error, which would actually give you the fact that L would be equals to roughly order of log of 1 by delta, and your B is 1 by epsilon. B we have seen why. For this L to be log of 1 by delta, I have to get into the error analysis, which I am skipping for now. But again the same kind of Chebyshev argument would work. But here there is a minimum thing which you have to handle very carefully. So, minimum would translate to an intersection, right. So, intersection you have independence, so you can look at products, each individual to the power of L. So, you will get to the power of L, and that is why you have a log term there. Right. So, this is what count mean sketch is. Any queries before I move into count sketch, where I will try to do the same thing using only a one dimensional array. Any queries? So, you know by now I think you can appreciate the power of independent trials. Now, if I am given only a single dimensional array, how I would simulate this is going to be a challenge. What do I do? Yeah, if you have queries, ask, or you have an idea, throw it out. Yeah, tell me. Variable bucket sizes. So, you want that would be a problematic thing. No, I have to hash. So, you think of this, your idea was possibly good, but you think of this. This bucket size has to be prefixed, because I am hashing from a universe to B. So, if you change this index, and x which was being hashed to a 100th location earlier might now hash to a 110th location, and then you are done, you are gone. So, B has to be prefixed. Once your algorithm, this epsilon delta parameters are given to you, this B has to be prefixed, because you cannot have a variable array, right. Then what? The only possible thing that might help me is as follows. Say I have an element x, which gets through this hash function, this suitably chosen hash function gets to this location. Now, by now you know that there would be y not equals to x, such that hy is equals to hx. So, this element y would also in fact there would be many such y's. So, let me mark them as y1, y2. So, there will be many such yi's which goes and disturbs the frequency of x. And as I am using only one unidimensional array, the only thing that can possibly save me is, what I would try to do is I would look into these contributions from this yi's and kind of attach a plus minus 1 random variable to it, and hope that some of the contributions from yi's would push up, some of the contributions from some other yi's would pull down, such that this entire sum would be equals to 0. So, I would think of attaching this, instead of adding up or taking minimum, what I would try to do is make these contributions that all other yi's make random, kind of plus minus 1 random, so that some of the frequencies add up, some of the frequencies subtract, on the expectation everything goes to 0 apart from the count of x, right. So, that is the idea we will try to implement. So, let me call this array CS and let its size be some k. You initialize this array elements to 0 as you start counting. Now, you have seen that in the case of count means sketch, the array size was 1 by epsilon. Here if you go through the analysis, this array size would be the size of the array in the one dimensional thing would kind of grow up, because your epsilon is less than 1. So, this cannot be avoided, right. Again, as I said, so I showed you for count means sketch how this 1 by epsilon thing was coming, right. How you remember this, right? This overestimate calculation actually was dictating the size of the number of buckets, the number of columns that you would have in the data structure, and the probability error was dictating the number of rows. So, in here what will happen is this overestimate thing, as because this is a unidimensional array and these epsilons are less than 1. So, you cannot but escape this 1 by epsilon square thing, right. So, again as I said, this calculation should dictate this 1 by epsilon square, and then what I do is I have, instead of one hash function, random hash function, I take now 2 random hash functions. Again my calculation would kind of fix the amount of independence that I require from the hash function. Choose another random hash function gn to plus minus 1 from a okay. Ensure one thing, ensure that the choice of G and H has nothing to do among themselves. Okay. So, what you now do, whenever you see a token, So, J belongs to this universe of size n, remember. What you do is for this array CS, you go to that location, so now it is no longer an increment, it is an addition of a random variable which can be either plus or minus 1. This might even work if the token has a weight, so you can multiply then the plus minus 1 with a weight. So, it would even work for weighted case. Anyway, so this is what I do. So, this is actually my increment step. Earlier what was just adding plus 1, now it is adding a random variable plus minus 1. Okay. So, what is my output? Now, in output I need to be a little bit cautious, because it might so happen that the quantity whose frequency I am wanting to count has gone through a very precarious sequence of updates such that this has always been minus 1, right. So, the output also cannot be whatever is there in the array. I have to also make it go through a multiplication with this GA, right. Why? Now, think of this, if this GA for a particular, I am not looking at a particular token. So, this GA is equals to say minus 1. Now, if on the output side I multiply it with GA again, then these two minus 1s should make it a plus 1. And if this was anyway plus 1, then that would also be plus 1, and then you would be doing fine. So, that is the idea. So, on output side what you do is so, this is the trick. The entire fun actually lies in this. Without this multiplication, I could not have proved unbiased estimator, which I will shortly do. So, what is the situation now in here? If you think in terms of the array, so you have this array CS, this count sketch array for a particular element I, say you have hashed it to a location say HI, and there are J1, J2, many such say JKs such that HI equals to HJ1, HI equals to HJ2, so on and so forth, HI equals to HJK. And but what you have done is this contribution that gets from J1, J2, Jk, they come with some with random plus 1, some with minus 1, right. So, all these contributions that go, they are not just a simple plus addition, they can be a minus addition, and you hope on the expectation they kind of cancels out. So, is the idea clear? Fine. Now, let us get into the analysis of the overestimate. So, fix a in sigma, and so let x be the random variable denoting the frequency estimate. Now, I fix an indicator random variable for all other tokens apart from A, which is equals to 1 if the hash value goes to A. The rest are all 0 because I do not need their contribution. So, for each token j in n, so let now notice this random variable. If it is a random variable, see, now in the analysis we have to be little cautious because now there are two sources of randomness, a randomness coming from H, a randomness coming from G. I have to be very particular about it. So, this randomness on the variable yj is coming from where? H, right. So, this is the source of randomness for yj. Fine. So, now I look at a token j. When I say contributes, it can mean either a positive contribution or a negative contribution. To the counter Cs HA, if and only if now what is the amount of the contribution that we have to fix? That is Fj, whatever is the frequency of j, and that comes with a, right, because whenever you are looking at a token j, it goes through a hash function g, so it either adds +1 or -1. So, this is the amount of contribution that the token j is giving to that particular location. So, what is your x? The final frequency. Mind you, x has contribution from A as well as different j's such that those j's had been hashed to this location of A with some random signs. So, that is j into gj, and I am only bothered about those j's whose hash value is equals to the hash value of A. So, that means this random variable takes care of that, because those don't hash has 0. So, I am done. Which one? Okay. So, what I am now looking at is, I am looking at a particular location of this array where I am trying to argue about the frequency estimate for a token A in the universe, right. So, you have fixed a token A. Now, this token A through this hash function h has gone to a particular location of the array. Now, I am looking at all other tokens in this stream that has also gone through this hash function h and has gone to the same location. So, this fixing the locations is taken care of by this indicator random variable, fine. Now, if you look into all those j's which has gone to the location of A, what is this contribution? It comes with its frequency, but not with its exact frequency, but multiplied with this random variable plus or minus 1, right. That was my algorithm, remember, go back to the algorithm. It came with this contribution. So, each time you are adding either a plus 1 or a minus 1. Agreed? But am I fully correct? No, this is j equals to 1 to n, A is within that. No, A is there, right, this is j equals to 1 to n, so I have taken everything. See, once you have fixed a token, this has hashed to a particular location. When it has hashed, it has gone with its sign, random sign, and that has been taken care of in here, right, because j equals to runs from 1 to n. So, A is in there. But the thing that I have missed is, when I reported for A, I not only reported this, but I also reported this random value GA, right. So, my estimate is actually GA into this. Now, see what has happened actually in this particular location corresponding to A, many other tokens have contributed with plus minus whatever. So, finally, there has been a value in there. Now, when a query has come for A, my algorithm says, so what is my algorithm now telling me? Telling me that look into that location, whatever the value is in there, plus minus whatever, multiply it with GA and then report, right, and x was the random variable capturing this value. So, x should be this. So, this is the full contribution, this part is this contribution in this CSHA, and this is this random variable GA with which it was being multiplied. Done? Right. Now, let us analyze this quantity. Now, first, so this is over j equals to 1 to n. So, let me now write this quantity as, so this x is for a particular A, right, for an A belonging to sigma. Now, what I am trying to now do is write this random variable as contribution from A and from the rest. Now, see the fun thing will happen. So, this sum is on j's which belongs to n minus A. So, the rest contribution, right. So, from this universe I remove A. So, this remains whatever it is, Fj into Gj into Yj. But for A, what are you getting? It's now become Ga into Fa into Ga into 1. What is Ga square? 1. That is the reason I took this random variable to be plus minus 1. The fun is actually there. So, this quantity is Ga square into Fa, right, because now J is equals to A and Yj is 1, right. So, this is nothing but Fa. That was the reason I multiplied it with G. So, the contribution of Fa will never come out as negative. The rest will come out as plus minus randomly and sort of cancel things out. Fine. Now, you start getting the fun of probability, right. You can do a lot many things. Okay. Now, let us even analyze this further. My final goal is to show that this x is an unbiased estimator. Oh, I do not have much time. So, I will not get into the variance part, but let us just show that this is an unbiased estimator. So, that means I need to show that this is what it was supposed to count. Okay. Now, so what I am taking is expectation on this x. Now, mind you, what is Fa? This is not an estimate. Fa is the exact frequency of A. So, this is a constant for my case. Once you fix a token, its frequency is what it is. Okay. So, an expectation of a constant is constant. So, this is Fa plus I use linearity of expectations. So, use linearity of expectations on this. I think I missed a term there, right? Oh, ho, 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 ho. You should have told me. I missed a term in here. See, in this contribution from rest, this was a sum multiplied with Ga, right. I took the contribution of Ga in this sum, but I did not take it for the other one. So, this is actually right. So, there was a Ga outside which I missed, right. So, this was an error. Okay. So, you are taking expectations over this. Use linearity of expectations. Now, see, these Fj's are constants. So, the frequencies are what they are. For this sum, Ga is also a constant, because in here this is for all j's minus A. So, A is a constant for it. So, you now look at a term which is a product of Now you are in a situation where you have to take expectation on a product of two quantities. One quantity is dependent on the randomness of G, and this, as we argued earlier, dependent on H, and initially I made H and G independent, right. So, now I can write this as the product of their individual expectations. Okay, let me not just write it just in one go. Now, so focus on this term, expectation of G of j into Yj. So, this I can write as expectation of Gj into of Yj. So, this is true for all j's not equals to a, fine, because your sum is indexed over all j's not equals to a. Okay. And why is this? Because G and H are independent. Now, what is this expectation? This expectation, what is this? This was, G was a random hash function between +1 and -1. So, it was spreading all elements j in your universe uniformly to two locations +-1. So, you add them up, that is your expectation. So, this is 0. So, whatever this expectation Yj might be, this entire quantity is 0. So, that means each such product is a 0. So, the entire sum is 0. So, this entire thing goes to 0. So, what you land up with is effect. So, this is an unbiased estimator. So, I would stop here. One can even do little bit more involved calculations using these facts to show that your variance is also nicely bounded, and you can get to a epsilon delta rather an algorithm which is like just fit for this median of means trick. And finally, one can show that now with the requirement of space 1 by epsilon square log of 1 by delta log m plus log n. So, this is your final space, right. So, I would stop here. Queries. So, variance would be even more fun calculations than this one, right. So, do not you find this algorithm to be nice? So, it nicely uses probability. So, the entire trick actually was dependent on that random function G uniformly distributing any token to either +1 or -1, and it was taken care well by this multiplication of Ga. Yeah, any queries? You have none.